Thanks. So today I want to speak about the prismatization and explain how it can be used to obtain proofs of the main comparison theorems that I've stated yesterday. And so let's fix a prime P. And I want to start with a nonsensical question, which then yields the right answer. So, and what is this question? It's what is the spectrum of the initial prism? And so this question is nonsensical as there does not exist an initial prism. And but let's for the moment forget this and try how we would access this spectrum. And so the first thing is that we would consider an oriented prism, because locally at least every prism is orientable, meaning the ideal I is the principal, and then we can also choose some generator. And now we can consider the initial oriented prism. And so how does it look like? So we have to consider the free delta ring on some element x, and this x should generate the prismatic ideal. But then we should also invert the element delta of x. Okay, and then we should also px adically complete this ring. So this is the initial oriented prism. And so what we would expect by the fact that each prism is locally orientable, that there exists at least a flat, or say Inzer-Risky locally Inzer-Risky surjection from the spiff of A0 to this hypothetical spectrum of the initial prism. And so we would also expect the following, namely if we try to understand the relations for these surjections, then so what is the ambiguity that we have by lifting, say, a morphism from a prism to here? So it's the choice of two generators of the prismatic ideal, but then of course, as this ideal is given by some non-zero divisors, the difference is a unit. And so therefore what we'd expect is that the that this fiber product identifies with, and here it seems reasonable to take the free delta ring on a unit. And so now okay, I have now derived this desiderata, and so now let's try to analyze what it gives. And
kind of a stack, it's more like a groupoid, or
exactly.
You know, there is a good quotient. You just say, okay.
Exactly. So, and the definition will eventually lead to the Cartier-Witt stack, and so that's then the right answer for this incorrect question. And so, in order to derive this, let's first analyze let's first analyze like the spiff of A0. And so for this, I want to note the following. Namely, as a functor on rings, the spectrum of the free delta ring on one element just identifies with a functor of p-typical Witt vectors. And similarly, the spectrum of the free delta ring on an invertible element just identifies with the units in the p-typical wet vectors seen as a functor on rings. And then as a functor now on nilb, which I use as the notation for the category, say, of rings R, whereas P are nilpotent, meaning that P is a nilpotent element in R. Also, this functor spiff of A0, it has the following form. So, spiff of A0, it will define a subfunctor of the spectrum of the free delta ring on X. And so, therefore, we can, using that description, also describe the subfunctor in terms of elements of the Witt vectors. And so, that's when the following. So, it's the functors, so it's a functor which associates to some ring R the following set, namely all the elements in the p-typical Witt vectors of R, such that the first coordinate A0 in R is nilpotent, and the element A1 is a unit. And so, let me prove this. So, let R be any ring. And then, what we have to analyze in the first claim is the set of ring homomorphisms from the free delta ring to R. But by the adjunction that I mentioned, that the forgetful functor from delta rings to rings has a right adjoint. This identifies with homomorphisms of delta rings from the free delta ring to the Witt vectors. And now I use the other adjunction, namely the free delta ring is the value of the left adjoint, and so that's the same as homomorphisms of rings from Zy to the Witt vectors of R. And so that's, of course, just given by the Witt vectors of R themselves. And so similarly, one proves the second part of the first claim. And so, yeah. Also,
so the first adjunction you explained before, or
pardon?
This the first isomorphism, this was in the previous?
I mentioned this in the first lecture, namely I've mentioned this result of Joyal, that the forgetful functor from delta rings to rings has left and a right adjoint, and that the right adjoint is given by the p-typical Witt vector functor.
So under this, the components of the Witt components of the Witt vectors, are they given by powers of delta or under?
I can explain how this works. So say A is a delta ring. And so then what we know that we have the following relation by definition, but one can also introduce higher powers of delta, so to say, operations of delta. And so what one can do, one can canonically write the nth power of the Frobenius as x to the p to the n times p to the delta of x to the power p n minus 1, and then p squared times an operation which is called delta 2 plus and so on, plus a last operation which is delta nx, And so actually these delta nx with a lower subscript are some monic polynomials in delta of x. And then, so in order to understand this adjunction, one needs to understand this unit map from A to the Witt vectors of A. And so it's given by as follows. So an element A is mapped to the following Witt vector. And so it's given by delta of A and then delta 2 of A and so on. So it's maybe not so easy how to express these in terms of delta, but just given these higher operators, one obtains this formula. And so that's also explaining why we have to put these two conditions there on A0 and A1. I mean, the condition on A0 comes from the fact that in A0 we've completed with respect to x. And the second condition, that A1 is a unit, it comes from the fact that we inverted the delta of x, which gives the first, the first component of the vectors. And so with the zeros, that's the first. So to say. And so now, given these,
so there in the definition it should be A1 belongs to
in this definition it's A1. You mean? And so now one can therefore make the following sensible definition. One can consider the stack quotient of A0 and by the action of the Witt vectors, of the units of the Witt vectors. And so given this functorial description, it's easy to see that the multiplication with the units in the Witt vectors preserve these conditions there. And so this gadget here, I take the stack quotient, is now a well-defined object, and it more or less serves as the spectrum of the initial prism. But now we can forget about these initial prisms and just work with this object. And we can also...
So implicitly you need a topology to speak about stacks. So which kind of topology, or do you have a freedom to choose? Or?
What I want is I consider these as functors on nilp, and then I take the FPQC topology. And so now, say if R is some adic ring over ZP, then I can consider the R-valued points of this Cartier-Witt stack, and by this I mean the homomorphisms of the spiff of R to W card. And so your spiff of R as a functor on nilp is given by continuous homomorphisms. And so then this set can be calculated, and it's given by the following data. So it's given by a morphism alpha from some WR module I to WR. So where actually this I is an invertible ideal for the Witt vectors of R, and locally on spec R, I is generated by some element in the Witt vectors which takes the form So locally, this map alpha is given by multiplication with some element in the Witt vectors of R, and so this element should have the form as required in the definition in that lemma. And so these gadgets are called also Cartier-Witt divisors. So one warning, this morphism alpha is not assumed to be injective, and that's actually a very nice feature. And therefore, when it's speaking about a generalized Cartier divisor, meaning just an invertible ideal with a map to the ring. And so now, okay, I motivated the introduction of the stack by the question, what is the initial prism? But now we should relate this actually to prisms. And so
A0 is the condition is just on A0. A0 is topologically nilpotent.
And A1 is a unit.
No, but then it's injective, no?
No, it's not necessarily injective.
If A1 is a unit, okay, I understand. Okay, because the ring is okay.
So how does the W cross act on this? Do the space? Because
you can multiply on I.
so on the alpha, so it's multiplied on all the.
Yes.
Okay.
So, but nilpotent or topologically nilpotent?
I mean here, this is seen as this is topologically nilpotent, yes, because I took R to be some adequate. And so now, given a prism A comma I, and so the identity lifts to the morphism of delta rings, which is which I call gamma, from A to the width vectors of A, and it has this concrete property that I mentioned before. So it sends like A to A, delta of A, and so on. And using this lift, one gets the following. So we get the canonical morphism, rho A, from the spiff of A to the Cartier-Witt stack. And so to give a morphism like this, we have to give an element in the sections of the Cartier-Witt stack over A. And so we can take here I tensored over A via gamma with the width vectors of A, and this maps to the width vectors of A. And so note, so if D is a generator of I, then like gamma of D is equal to D and then delta of D. And so we see that these conditions are satisfied. D is topologically nilpotent and that thing is a unit. And now the precise formulation of how this Cartier-Witt stack is the initial prism is part of the following proposition. So assume we have two prisms, say, which are bounded, that AI is transversal, and then in the category of prisms there exists the product and here, so maybe note that the category of prisms is actually just the absolute prismatic side of ZP. And then we have induced morphisms of this form. I mean, this follows from the naturality of these morphisms rho B. And so actually this diagram is Cartesian. And so at least under the assumption that that one of these factors is transversal, the Cartier-Witt stack realizes, so to say, the initial prism, although it's a stack and so on. And then if AI is transversal and say A is not empty, not zero, then this morphism rho A is faithfully flat. And then thirdly, if we consider now quasi-coherent sheaves on the Cartier-Witt stack, and so what do I mean by this? So it's defined to be the inverse limit.
This means representable by faithfully flat. Is it faithfully flat in the sense that after any pullback, it is completely faithful, modulo ideal definition, it is faithfully flat in the usual sense, yes?
Exactly. So in particular, this contains the statement that this morphism is representable in formal schemes. Okay, and so how do quasi-coherent sheaves on this Cartier-Witt stack look like? So first of all, what is their definition? So I consider all morphisms of nilpotent rings to the Cartier-Witt stack, and then I take in infinity categories the inverse limit of the derived category for R. And so this is equivalent to the following gadget, namely I can take the inverse limit over all prisms AI and then consider the inverse limit over the PI complete derived infinity category of A. And so this gadget here on the right hand side, this is also what should be called prismatic crystals. On the absolute prismatic side of ZP. And so in particular, the cohomology of the Cartier-Witt stack with coefficients in O calculates the prismatic cohomology of the prismatic structure sheaf on the absolute prismatic side. Okay, let me indicate how the statement can be proven. And so, in order to, let's check this first statement, but that claim here is actually local on SPIF B and local on SPIF A, and using that the fiber products in the prismatic side are just computed on the underlying tensor product, one can reduce to the case that actually A is equal to B and that B is equal to A0. So that all of these are given by A0, just because locally we can factor these morphisms over the SPIF of A0. So in the end, what we then can calculate is that SPIF of C, so C is the product in the prismatic side of A0 with itself, but that's just given by the SPIF of A0 times the SPIF of this free delta ring on a unit. Again, the argument is that the product in the prismatic side, so what does it represent? It represents the choice of two generators for I, and these differ by a unit. And so therefore, it's represented by that thing. But that, exactly by the definition of the Cartier-Witt stack, identifies with this fiber product.
But you assume that AI is transversal. So once you do this, you can pass to arbitrary A and B.
Yes.
Even without transfer, I don't know. So because you have fiber product, you said in general, or?
Because at least one has products, so one has fiber products in general in the prismatic side, say at least if one of the two prisms is transversal. So when, more precisely, when there is no issue with torsion appearing, if one of the factors is transversal, and when the fiber products commute with the functor to formal schemes.
So it is a formal scheme fiber product.
Yes. If at least one of the factors is transversal.
One of the two.
Yes.
Not the one.
Okay. And so let me indicate how one proves the second statement. Namely, the second statement is a consequence of this of the key technical statement from last time. So and here I mean this statement last time on prismatic envelopes. So there the statement concerned the pi complete flatness of certain prismatic envelopes, and when translated into this situation, it implies that this morphism is, say, faithfully flat if A is transversal, and then a small argument then also shows that it's actually faithfully flat if A is non-zero. And so then the third point follows from flat descent, because in order how one can calculate when the quasi-derived category of quasi-coherent sheaves on the Cartier-Witt stack by choosing some flat surjection where we can take any transversal prism, and then the resulting Chesnev will by this property exactly calculate the Chesnev, which would also calculate the category of prismatic crystals. So here one can also use that one has descent in the pi completely flat topology for these prisms, for the derived categories of pi complete complexes on a prism. And so what I want to do now is I want to illustrate how this approach can be used in order to calculate prismatic cohomology in the absolute case for ZP. And so if we want to calculate the prismatic cohomology now of a reduced prismatic structure sheaf, then this identifies with the cohomology of the so-called Hodge-Tate locus in the Cartier-Witt stack. And so what is the Hodge-Tate locus? It's the locus in the Cartier-Witt stack where A0 is 0, and another way how to understand it or access it is that if one takes the Cartier-Witt stack, the Hodge-Tate stack, and the fiber product with over the Cartier-Witt stack with any spiff of A, where this morphism is coming from like AI is a prism, and when you consider here rho A, the canonical morphism, then this identifies with the spiff of A mod I. And so in order to calculate now this reduced prismatic cohomology, and note that because this is happening on the absolute side, there's no Hodge-Tate comparison theorem. So that's something different that we now have to understand. And in order to calculate this, of course, we should analyze this hot state locus. And this can be done as follows. So let's write down some canonical point of this hot state locus. Namely, so we have, I want to define a morphism from the spiff of ZP to the hot state locus. And so now this means that we have to give a Cartier-Witt divisor for ZP, which has a first, like, zeroth component 0. But then what we can do is we can just consider the multiplication by the element V of 1. So that's clearly a Cartier-Witt divisor. And so we can consider this morphism. And the claim is that this is faithfully flat. And the proof works as follows. So
it is not so readable because of the shadow. V.
Okay. So in order to check that this morphism is faithfully flat, what do we have to take? We have to take any point in the hot state locus, and so the respective point, by the assumption on factoring through the hot state locus, will have a property that it's given by, at least locally, by multiplication with the element V of U, where U is a unit inside the Witt vectors of R. And so now note that we have a following equation. So V of U times X is equal to V of F of X times U. And so what we want to find some X such that this expression here is equal to 1, because then the multiplication by X will identify this Cartier-Witt divisor with the one V of 1. And so in order to achieve this, we have to find some X which is such that F of X is is equal to U inverse. And so now what one can observe is that with Frobenius, as a morphism from the formal scheme of units and the Witt vectors to itself, is faithfully flat. So this faithfully flatness in turn reduces to the faithfully flatness of the Frobenius on the scheme of Witt vectors itself. But then one can actually use that, okay, the Witt vectors were defined now on actually over spec Z. And then after inverting P, the Frobenius identifies just with a shift map. And then modulo P, it identifies with raising to the P power in each coordinate. But this is basically the Frobenius on some affine space, and therefore faithfully flat. And so now we have this faithfully flat surjection, and this implies that this stack is the quotient of this morphism by the automorphisms of the multiplication with V1. And so now one can understand these automorphisms explicitly. So the sheaf of automorphisms of eta identifies with the F torsion in the units in the functor of units in the Witt vectors. So these are the elements X in the units of the Witt vectors, such that F of X is equal to 1. And okay, when we are here, we can also identify the following, namely the kernel of a multiplication by V1 on the Witt vectors is given by the F torsion of the Frobenius on the Witt vector. So it's given by X in W such that f of x is equal to 0. And so the proof of these statements is very easy. Namely, it just follows from this equation that we already used. X times v1 is equal to v of f of x times 1. So, and therefore, the automorphisms of the multiplication by v1 identify with the x such that f of x here is equal to 1. Okay. But in order to be fully useful, one should understand these groups further, and this can be done.
V is injected.
V is inject, yeah, yes. V is injective as a map from the Witt vectors to itself, but not the multiplication by V of 1. And so this group scheme there, it identifies with GM sharp, which is the spiff of the following ring. So completed direct sum of ZP times T minus 1 over n factorial to the power n. So in other words, that's the PD hull of the unit section of GM, yes, P completed GM here. And so in particular, this Cartier-Witt stack, the hot state locus in the Cartier-Witt stack identifies with a classifying stack for this group scheme. And similarly, one can also identify this F torsion in the Witt vectors. It's given by GA sharp, so which is the spiff of the completed direct sum ZP of AN over n factorial. So it's the PD hull of the unit section in GA. And so for the proof, so 1 is slightly more complicated than 2, and so we'll indicate how one proves 2. And so, because that can be done directly, so by the definition, this group scheme, it's the fiber product of the unit section in the Witt vectors, and then with the Frobenius of the Witt vectors. And so, in terms, this implies that these F torsion points in W identify with the spiff of the following. So we take, so W is represented by the free delta ring on one element. So we take that thing, we tensor with ZP, and we tensor over ZPX. And so here X must map to phi of Y, and here X must map to 0, but also all the deltas of X then must map to 0. So and so recall that this is just a polynomial ring on X delta squared X, and so on. And so this implies that this is isomorphic to the spiff of the following ring, namely we take Y0, Y1, and so on, and then P complete, of course, and we have to mod out Y0 to the P plus P Y1, and then Y1 to the P plus p times y2 and so on. And then just inspecting this quotient shows that this is isomorphic to GA sharp. And so, okay, yes. And so now that's just as a scheme, but then one can use the following. So in order to check that this is actually an isomorphism of group schemes, it's sufficient here to show that it lies over the natural map that both of these schemes have to GA by flatness of these two guys over ZP, and then one reduces to the fact that in the zeroth component the Z vector addition is just the usual one. And so the argument for that finishes the argument for 2, and the argument for 1 is slightly more complicated because here that quotient that one has to take, so meaning x mapping to 1 is more complicated. Okay, but anyway, this proposition would not be very useful if these group schemes are very complicated. And so these group schemes, they are, say, incentomic, so they are not of finite type. This may look as if they are complicated, but what is very nice about these group schemes is the following. So if we consider the derived category of quasi-coherent sheaves on this formal stack, then this has a very concrete description, namely it's given by pairs M in the p-completed derived category of ZP and theta, which is just an endomorphism of M with the following condition. So theta of p minus theta is locally nilpotent on the cohomology of ZP modulo Fp on M modulo P. And similarly, the derived category of B of GA sharp identifies also with pairs M and theta, but now not theta P minus P is locally nilpotent, but just theta. And this statement is not very difficult to prove, but for reasons of time, I want to concentrate on showing the second part and say only for vector bundles. And so, what's the argument that one can give? So, let us define A to be O of G A sharp. So that's Hopf algebra over ZP.
So in 2 the condition is what? Is just the theta is locally important.
Exactly. And so what we can do is we can consider the dual of this Hopf algebra. And so this, because of the divided powers in the definition of O of GA sharp, the dual will just be a power series algebra. And let's call the generator theta. And so now if M is a finite free module, over ZP, then the following are equivalent, namely to give a coaction via this Hopf algebra A. Okay, and now note that this M tensor A can just be written as continuous homomorphisms from B to M. And so now we can just use a junction and put this on the other side, and therefore see that this is equivalent to an action B tensor over ZP with M to M. Okay, but we have to take care of this continuity condition, and this just translates into the condition that theta is topologically nilpotent. On M. And so maybe one remark on the relation of these two group schemes. So one has a short exact sequence of group schemes of the following form. So by the existence of these divided powers, one has a canonical logarithm map from GM sharp to GA sharp, and one can actually check that this is surjective and that the kernel is spanned by mu p. And so now passing to the Cartier duals, one sees that one gets on the Cartier dual a factor z mod p appearing, or quotient z mod p, and z mod p is exactly like fp is just the vanishing locus of this polynomial, and so therefore one sees that the difference between these two representations is governed by summary fp, and that explains the appearance of this polynomial theta p minus theta. And so as a corollary, we get the following. Namely, we can now just calculate the prismatic cohomology, the reduced prismatic cohomology of ZP. Namely, so of course the ideal sheaf on, so how can we do this? So that's the same as the cohomology of the hot state locus, and that's the same as the cohomology of this like group scheme, but with coefficients in ZP. But this is just given by the two-term complex ZP via 0 to ZP. Why? Just out of this, this just follows from this equivalence of categories here. I mean, one has to understand the endomorphisms of the unit, and so then, or more generally, the cohomology of such a guy is given by the two-term complex M mapping to M via theta. And so this is what I wanted to say about the application of the Cartier-Witt stack for the prismatic cohomology, the absolute one of ZB. And so now I want to pass to more of a relative say. Okay, so I want to extend the situation to R being some p-complete ring. And so note that if we take now some object in the absolute prismatic side of R, then let again be gamma be the lifting, the canonical lifting of the identity from B to the vectors. And then what we get is the following. So by definition, we have a map from R to B mod J. And so B mod J maps to B mod J tensored derived over B with via gamma with the width vectors of B. And so that is just the cone of the morphism J tensored with B with the width vectors of B. And so we get here a morphism from R to there, and that's actually a morphism of animated rings. And so this motivates the following definition, which is the definition of prismatization. So there are some notations for it. So one can use, say, R upper prism to, or also the notation is W card lower script R. And in any case, it's the stack on nib such that R prism of S is given by the following groupoid. Namely, we consider Cartier-Witt divisor on S together with a morphism of R to the cone of alpha, and this is a morphism of animated rings. So here one has to check that actually the this cone is canonically an animated ring, which follows from the fact that this is invertible. I mean, this complex basically represents a DGA, and so that's the cone. And so, in particular, just the prismatization of ZP is just with a Cartier-Witt stack that I've introduced before. And so this gadget here, the prismatization, is meant to capture the absolute prismatic side of R.
So here you are working in some infinity categorical sense. I mean, when you speak about morphism, yes.
Exactly.
But is it stuck in the normal sense, that is for every, it is a category, one category, I mean, what you get is a category without higher.
This is this category,
Yes.
a priori infinity, is a groupoid.
A usual groupoid.
Yes.
Okay. One groupoid. Okay.
Yes. And so to get the relative situation, one takes the following. So assume that AI is some prism and that R is some A mod I algebra. Then what we can define as the relative prismatization, and it's defined to be the fiber product of the prismatization of R over the prismatization of ZP, which is just the Cartier-Witt stack. And here we take this canonical morphism rho A from the spliff of A to the Cartier-Witt stack.
Sorry, but why is it a one groupoid?
Why is it a groupoid? I mean, how do the automorphisms look like? So we have automorphisms of the Cartier-Witt divisors. So these are given by multiplication on the ideal I. And then this cone of alpha, I mean, it just has homotopy groups in degree 0 and 1, and when the morphisms from R, I mean R is a discrete ring, to that thing, I mean there also only exist isomorphisms which are given by derivations, basically. And so, generalizing the theorem that I've stated before for the prismatization of ZP, one has the following statements. Okay, so first of all, that's actually a new feature. So one can make this prismatization explicit in a large class of cases, and so that's the following. So if you assume that R is quasi-regular, semi-perfectoid, so what does this mean? This means that R is quasi-symptomic, and there exists a surjection from some perfectoid ring. When the prismatization R0 is perfectoid, exactly, yeah, thanks. And so when the prismatization of R is just represented by the spiff of prism of R, and so here the prism of R, what is it? It's the prism of R relative to A inf of R0 for any choice of R0. One can actually take any choice of perfect base prism to calculate this. This does not change the resulting derived prismatic cohomology. This follows from the fact that the cotangent complex of a map between perfectoids is trivial. And so therefore, by the state comparison, if one has a natural map between like this relative prismatization for R relative to 1, perfectoid base prism to another, then this is an isomorphism by the hot state comparison. And then secondly, so if R is quasi-symptomic, then the derived category of quasi-coherent sheaves on this prismatization, equally defined via some inverse limit of infinity category, is equivalent to the category of prismatic crystals on the absolute prismatic side. And so in particular, the cohomology of this prismatization calculates the absolute prismatic cohomology of R. And then, if I is, say, a bounded prism, and one assumes that A mod I to R is quasi-symptomic, then the quasi-coherent sheaves on this relative prismatization identify with a derived category of prismatic crystals on the relative prismatic side. And so the proof for this I just sketch orally. So first, one needs to understand in this case the case for a perfectoid ring and see that here when the prismatization is given by the spiff of A inf. And this follows from derived deformation theory using that the A inf of a perfectoid ring has trivial cotangent complex over ZP. From here, okay, it's not direct to reduce the quasi-regular semi-perfectoid case, but at least it's one can make this identification if this quotient from R0 to R is given by, say, some infinite regular sequence, because when using prismatic envelopes, that guy here is can be explicitly described, and when one checks that both are the same, and then one needs some reduction to get the general case. Then the second case, the second claim, it follows from the first one by quasi-symptomic descent, because given this isomorphism, I mean, it's clear how to describe the quasi-coherent sheaves here. And similarly also the third point, using then a relative version of the first statement, replacing quasi-regular semi-perfectoid algebras by large algebras. And so what I want to address now is why is the prismatization useful? And so basically the prismatization is a theory which is equivalent to like prismatic sites and prismatic cohomology, but some things are easier to see using the prismatization. And so, and this mostly follows from the following, namely, there exists a natural ring stack R over W card, so meaning the prismatization of ZP. And so how is it defined? So a ring stack over W card means that for each nilpotent ring with a map to W card, we have to define some ring stack, and so some ring groupoid. And this can be done as follows, namely, a ring groupoid associated to RS for some S-valued point of the Cartier-Witt stack is just defined to be the cone of alpha. And so in fact, this ring stack can also be seen as the prismatization of the affine line. And so the ring stack structure is then induced here by like the co-ring structure of that guy.
So a ring stack means a stack which has operations of addition and multiplication satisfying the ring axiom up to equivalences which satisfy some coherencies and so on.
Exactly.
And your ring means commutative unital ring here, so?
Another way how to see, to think about this, it's a functor it's a functor on NILP with values in animated rings, which are constant, which have a property that their homotopy is concentrated in degree 0 and 1. And so now, given RP complete, when the prismatization of R evaluated on S, so where S is now some object, some p-nilpotent ring with a morphism to W card, this is just determined by this ring stack, namely, and this is just the definition, namely, we take ring, the morphism of ring groupoids from R to R evaluated at S. And so now the power of the prismatization is that this ring stack, which governs the theory, can in certain situations be made more accessible, which then yields comparison theorems.
So this original R is kind of we take the unidie embedding of the R into this unimportant ring.
Say again?
The first R, right? No, in the home, right? Yeah, in the home. Yeah. This R is the unidie embedding of the ring R into this functor of unimportant ring.
I think I don't understand. Like what I'm taking here is, so RS by definition is a ring groupoid. And in particular, every ring should be a ring groupoid. And so I take homomorphisms here in this category of ring groupoids.
But it's all over W curve, so it's a bit confusing.
Sorry.
Like you say, R is a ring set on over W curve.
Yes.
So somehow, and with RFS, you implicitly pick a point.
But this is why I wrote here that S is in nib over W card.
Can you have a ring stack which is not a stack in groupoids? Or when you define a ring stack, you can define it without requiring that it is a stack of groupoids? Or
No, but this R is a stack for the FPQC topology.
No, but is it the case that the notion of a ring stack makes sense without assuming it's a stack in groupoids? There are ring stacks which are not.
No, I don't think so. Okay. Now I think I understand. I mean, one can always take a functor from, say, nib to animated rings without requiring this boundedness condition on the animated ring.
Okay, okay, I will ask you later.
And so one example which I now want to discuss is the following. So I denote R DRAM, the base change of this ring stack over W card to spiff set P W card, where this morphism from spiff set P to W card is given by the Cartevit divisor, which is just the element P. And so maybe why is the element P inside ZP a Cartevit divisor? I think that's easiest to see using the reduction to the Witt vectors of Fp, and there inside here one has the equality that P is equal to V1. And so therefore this P will be a Cartevit divisor for Zp.
Sorry, it should be of Prismatization.
Sorry?
In the fiber product.
Here? No, I think that's exactly what I want.
No, I mean in the right.
That's the ring set.
Sorry. Okay. And so now this ring stack can be written down more explicitly. Namely, it's given by GA modulo GA sharp over spiff of ZP. And the proof here can be given as follows. So GA mod GA sharp, I can write as a functor on nilp as the quotient of vivid vectors modulo the Verschiebung of vivid vectors. And so therefore this quotient here identifies with W modulo V of W plus GA sharp. And so now what I can do, so one has a natural map from here to there. And so now what I can also do, I can apply the Frobenius to that thing. So that's a faithfully flat map. And so it has the property that it kills this vector GA sharp. And so therefore, what we obtain is that this ring stack is isomorphic to W modulo F of V of W, but that's just isomorphic to W modulo P, but that guy is just this ring stack R DRAM. Just from the definition of this point P, namely the ring stack, it's given by the multiplication by P on W. And of course here, what I mean is this quotient in the derived sense. And so as a corollary, one gets the following. So if K is a perfect field, K to R is smooth, then the Frobenius pullback of the prismatic cohomology of R relative to the Witt vectors of K is isomorphic to the crystalline cohomology of R over W of K. And so the proof is as follows. So the prismatic cohomology of R relative to WK, we can calculate it as the cohomology of the prismatization of R relative to WK. And so this I can, now I plug in the definition. So I take, let's say now R gamma of Hom of R to R DRAM, base changed to WK. So here, with this notation, I want to indicate the stack on nilp of Witt vectors of K, so that its S-valued points are given by Homs from R to R DRAM evaluated on S, and these are Homs of a ring groupoids of O. But now that's isomorphic to R gamma of Hom of R to this other stack over there. With O, and now seen as a stack over the Witt vectors of K. And so now, note the following. So this Frobenius twist which appears here comes from just looking at the WK linear structure of this isomorphism. But here, in this guy can, as a functor on WK, has its WK natural WK linear structure, but also this guy here has. But because one has applied the Frobenius here, one has to also include the Frobenius twist here. But just for calculating the cohomology, neglecting the WK linear structure, one does not have to put some Frobeniuses here. And so, and now, if say R is a smooth lift of R to WK, so more precisely P completely smooth, then one checks that the spiff of R tilde maps via a flat surjection to this ring stack that I've written down here. So that's, I can say, application of, say, formal smoothness. And so the Chesnev is given by PD envelopes of the diagonals. And so thus, the complex with which one would calculate the cohomology of this stack by this cover just identifies with the crystalline cohomology, or like with the derived cohomology of R tilde. And so this in the end is therefore isomorphic to the crystalline cohomology of R relative to W of K.
What's happening in the from the first line to the second one? Can you replace this with the hum? Yeah.
That's the definition of.
Up there was no derived, right? It was just R.
Yes, but the following. So, how did we define the relative prismatization? It was via the map from WK to W card, but this just factors over this map here. And so therefore, the ring stack underlying the relative prismatization for WK is just the base change of this R DRAM. And so let me indicate another application. So AI should be a bounded prism. And what I'm aiming at is now the Hodge-Tate comparison. And for this, what we should do, we should understand the ring stack R Hodge-Tate, which is defined to be spiff of AI, fiber product over W card with this ring stack R. So that's now a ring stack over spiff of A mod I. And so as such, one can, okay, again, the strategy is to make this ring stack explicit. And this can be done as follows. So there exists a natural morphism.
You actually take the fiber of Hodge-Tate stack, because now there's A on the right hand side. So
yes, yes. I mean, you can also write this as spiff of A mod I W card Hodge-Tate, and then do you like say restrict this here to the hot state locus. This does not change the fiber product.
Okay.
The objection was that you could put A in the notation for A.
Ah, yeah, sure. Okay, yeah, sure. Yeah, but I want to shorten it. Okay, yeah, sure. Yeah. And so we have a natural morphism of ring stacks R hot state maps to GA. Of course, GA is, I mean, it's just a ring, a sheaf of rings. And so, and whose kernel is GA sharp, Cartesian twisted ones and shifted ones. So here, this makes sense. I mean, that's a sheaf on, that's like a derived sheaf on nilpotent rings over A mod I. And when, because, I mean, this is happening in sheaves on nilp of AI, and also there one can speak about the square zero extension of, say, some animated, some sheaf of animated rings. And so therefore this is well defined. And namely because what I wanted to say is that this kernel, meaning the fiber of this map, is a square zero ideal. And so for the proof.
So what does it mean square zero in this case of ring stack? So it is like simplicial rings with two terms, but what does it mean square zero? It is yeah.
That notion is it's just the notion of a square zero extension of animated rings, but in functors on nilp. So one can reduce this question to the question, what is a square zero extension of animated rings? And so, so for the square zero extension, we also give the idea. And so say we have an animated ring C0, C and a ring C0. And say the fiber is given by some C0 module M. And then the property of being like the data of a square zero extension is when a pullback square, the following form, so here one takes like the morphism identity 0, and here one takes any morphism which is the identity in the first component. So it's given by some identity and delta, and then the datum of a square zero extension of animated rings is a pullback square like this.
So is it a condition on C to C0 also with an extra data?
It's an extra datum. Like it's not just the fiber sequence, but it's also like this pullback square.
Okay, so for usual rings in degree 0 it's just a condition, and in general it is in some sense an extra datum.
Yes.
So it is like
and so where does this square zero extension come from? It comes from the fact in the end that if you have an animated ring which has only pi 0 and pi 1, then this animated ring is like an extension of its pi 0 by pi 1. And so let's consider like pi 0 of R hot state evaluated on S. And so what is this? This is given by the width vectors of S, but modulo V1 times Vs. So note that this admits a natural map down to S, which is given by the width vectors of S modulo V of the width vectors. And so actually because this is happening as sheaves on nilpotent rings over A mod I. In order to, we should not just look at this morphism, but we should view it as a morphism of presheaves. But then, if we pass to, say, faithfully flat extensions of S, then we can actually see that this becomes an isomorphism. If we sufficiently, like the point is that V1 of WS is the same as V of F of WS. And so at least faithfully flat locally, these two guys agree, and therefore they agree as sheaves. Okay, so this clarifies the pi 0, and now the pi 1. The pi 1 of that thing, it identifies with I modulo I squared, tensored over A mod I, with with the kernel of a multiplication by V1 on the Witt vectors, but this we saw is just given by W and then the F torsion points evaluated on S. And so that's the same as G1 GA sharp Tate twisted 1 evaluated on S. And so therefore the the kernel of the square zero extension is given by a shift of that sheaf, which I've written here. And so the corollary is now the following. So assume R to A mod I is smooth. And let me set A bar to be equal to A mod I. And when the relative Hodge-Tate prismatization of R over A, meaning restricting the relative prismatization to the Hodge-Tate locus, this maps to the spiff of R, just because one has this morphism of R Hodge-Tate to GA. And so this is a gerb banded by some group, which is a flat group scheme over R, and it's the following. So it's denoted TR over A bar sharp Bragg-Keesin twisted 1. And so what is it? It's the PD hull of the zero section in the tangent bundle, in the twisted tangent bundle of R over A bar. And so what is this? That's the spiff of the p-completed symmetric algebra over R of omega 1 of R over A bar, and then here Bragg-Keesin twisted by -1. And so therefore, how do we pass to the PD hull of some geometric vector bundle? We just replace the sum here by the divided power algebra. So locally, that group is isomorphic to a product of GA sharps. In particular, one understands its representation theory. And so the proof is derived deformation theory. Namely, just if one considers morphisms into a square sphere extension and one fixes the morphism to the base, then one knows that all the other morphisms form a principal homogeneous space under the derivations, and the derivations are homomorphisms from omega 1, and so therefore one sees that in this case here one gets a simply transitive action, but because of a shift 1 appearing there, it's actually a gerb, meaning like a torso under the classifying stack for this group scheme. And then as a corollary, one gets that the prismatic cohomology, the reduced prismatic cohomology of R over A is just isomorphic to omega I R over A bar, Tate twisted, Brachisian twisted minus I. And so how does this follow? Like that thing is a gerb over that thing. One wants to understand the cohomology, but okay, it's a gerb under this group, and then it's a general property that at least the HI is canonically isomorphic to the HI of the trivial gerb. But so this reduces the claim to understanding the cohomology of the classifying stack for this gerb. But note that this is just a product of GAs, and so we understood the representation theory for for GA sharp, and so doing like more or less the same for this product then shows that this cohomology is just calculated by the following complex, like it's calculated by, say, O mapping to omega 1 via the trivial differential, and so on. Like that, a complex like this calculates the cohomology on the classifying stack for that thing. And so that's how one can then prove the Hodge-Tate comparison theorem using the prismatization.
Why the differential at 0? The differential at 0?
Just consider the case, say, for GA sharp, and then the derived category here identified with pairs m theta. And so the cohomology under this correspondence, the cohomology of such an object is just given by that thing. And now if you plug in here m to be the unit, then like just the trivial representation, then the theta is 0.
You're basically using...
Yes, exactly. Just a version of that statement over there for not just GA sharp, but for the tangent bundle here, and then this appears. I mean, I can maybe, that's interesting to know anyway. So if I consider the derived category of that guy, then this identifies with the following. So M is an object in the completed category for R, and theta is now a Higgs field. So that's M mapping to omega 1 A sharp is 1 tensored over R with M, and I have to. So this is an R-linear map, and it satisfies that theta wedge theta is equal to 0.
So this equal to 0 is a datum.
Yes.
And does it satisfy some coherencies also? When you take theta 3 and you say, I don't know if it makes sense here, but...
Yes, so therefore, what I've written here is not the exact description that for example, used in the paper with Arthur and Ben, but one can one can make this precise, this condition, by viewing this as a subcategory of the just modules under the symmetric algebra of the dual of, so TRA bar should denote the dual should denote the dual vector bundle, and then here I'm viewing this as a I mean, one has to put the condition that theta is here topological nilpotent as well. And then the way how to make these coherences precise can be done by viewing this as a full subcategory in the category of modules over this symmetric algebra. And then one has the notion of just the module categories for some ring. I mean, it's just the derived category of this ring.
Okay, so this takes care of the theta with theta. Okay. And I think you wrote something in the beginning. There was a confusing R, instead of R to A mod I smooth, you mean the other way.
Exactly. Yeah, so that's what I wanted to present today.
Any questions for Johannes?
Actually, in that, you say that R quiescent and DR prism is the same as prismatic crystals on R prisms. Then, is there a way to let go of this quiescent condition?
Yes. Basically, all these statements extend to all animated P-complete rings using a derived prismatization, where one defines the derived prismatization using basically the same definition, but where now also the S is allowed to be an animated ring. And of course, one then has to make sense of the width vectors, but when one gets the derived prismatization, and then the story extends. But then one, of course, one also has to replace the prismatic side by something derived.
Any other questions?
Okay, I don't know. Okay. So for square zero extension, so you have naive square zero extension of simplicial ring, cumulative simplicial rings, that is square zero each degree. I suppose this gives you a square zero extension in your sense. And conversely, if you have a square zero extension in your sense, can it be always represented by a naive square zero extension? Or?
If I'm not mistaken, the answer is yes. Like when the category of square zero extensions, I think the animation of the square zero extensions for usual rings. I think, if I'm not mistaken.
That was the question.
Okay.
So is it easy to see that the matrons for tilde to the projection directly?
I think it's okay. Yeah. I mean, yeah. But okay, of course, to get the details, I would have to think about it. Like, for example, if you replace GL sharp by just the formal GA and look at the de Rham-Steck in characteristic 0, then this is like literally just the formal smoothness.
Mm-hmm. Okay, let's thank Johannes.